So we're going to look at calculating the percent impedance and available short circuit current of a single phase transformer. So I got an example here, and we've got a 9 kVA transformer. Its voltage rating is 480 to 120 volt. So we're using it as a step down transformer. It's single phase 60 hertz. A short circuit test was done and the voltmeter reading was 11 volts. So if you recall on the short circuit test, what we do is we put an amp meter here in the secondary, right here, and we just create a short circuit between X1 and X2 here. Okay, and then I slowly turn up this voltage supply, and when I get rated current flow through the amp meter on the secondary, I stop because I don't want to overload the transformer. Right where I stop, that amount of voltage here, in our case it's 11 volts, that was what we would call our impedance voltage. All right, so that's the actual impedance voltage. And we could say that 11 volts is required to overcome the internal impedance of this transformer when it's in a short circuit condition. So, or that's how much its impedance voltage is. So a couple of questions. We're going to calculate the percent impedance. So how we write that out is percent Z or percent IZ. You'll see that often stamped on the nameplate of a transformer. Okay. And what is the maximum available short circuit current? So the transformers have their kVA rating, and of course that corresponds to a maximum secondary current, and it'll correspond to the maximum primary current as well. But that's under regular operations, what we should load it up to without overheating it. Now if I have a dead short on the secondary, the current is going to go much higher than its rated current. And that's what we're going to do, is determine how high can it go. What's the maximum current that can output during a short circuit? So let's start with number one there, calculate the percent IZ, and we have this formula. So if we know our impedance voltage and we know our rated primary voltage, we can calculate the percent impedance of this transformer. So in this case, it's 11 volts divided by 480 volts, and then times that by 100, and that works out to roughly 2.29%. All right, so the percent impedance of this transformer, 2.29%. Take our impedance voltage, divide it by our rated primary voltage, and times it by 100, and you get your percent impedance of the transformer. So for a short circuit current, calculate the maximum available short circuit current on the secondary here. We use that percentized Z in this formula. So percent impedance is there. So what we need still is the rated secondary current. So we just got to go look at, we have a 9 kVA transformer. All right, so we take our VA, 9,000. And I want to calculate my secondary rated current, so I divide it by my secondary voltage, which is 120. And that comes to about 75 amps. Okay, so now I've got my rated secondary current. I've got my percent IZ. I can go ahead and calculate my available short circuit current. So I'm going to put that in there right now, 75 amps divided by 0.0229. So I express that as a decimal. And that works out to about 2,586.2 amps. So it can put up over 2,500 amps in a short circuit condition. Now, when we look at an overcurrent, why is this maximum available short circuit current important to us? If we look at an overcurrent device, they're going to have two ratings. So if I just drop a simple little fuse here, okay. So there's a fuse. It's going to have its continuous rating, right? So 15 amps, let's say. And then it's going to have an IC rating, its interrupting capacity. And the standard interrupting capacity is 10,000 or 10 kA amps. Okay, so 10,000 amps. And what that interrupting capacity is, it can safely interrupt a fault current as high as 10,000 amps without destroying anything or destroying itself or fusing together. In the case of a circuit breaker, it may just weld right where it is. The contacts aren't capable of opening it. It might weld them together. So the manufacturer says it can safely interrupt 10 kA, so the IC rating, interrupting capacity. So in our case here, our transformer can only put out 2,586 amps. So a normal standard fuse is fine. We could put that on there. But what happened if we have a very large kVA transformer, so it had a large secondary current, and it had a really low percent IZ, right? Really low percent impedance. Well, in that case, that fault current may end up being higher than 10,000 amps. So we would have to size our overcurrent. So it could be a 15, could be 100 or whatever according to our branch circuit. But we also have to make sure that the interrupting rating is larger than what our capable fault current of our transformer is. So it has to be larger. So I just pulled up a little chart that's coming up. It's talking about fuses here. And if we look at different classes of fuses, so a class H fuse, for example, it's got a 10,000 amp interrupting capacity. The continuous ampere rating of 1 to 600, like there's a variety of them. You can buy tons of these different ones. And if you look at some of these different classes of fuse, so like they go with a class J here, in that case, it's a 200 kiloamp interrupting capacity. So depending on the type of transformer you're using or the network of transformers when they're put in parallel, you may have an extremely large fault current available for our end. So we're going to want to make sure that the interrupting capacity of our overcurrent devices is capable of interrupting the available fault current of our transformer. Okay, so I hope that helped, and we'll see you on the next video.